There we go. Okay, welcome to the first demo lecture in TEP4280. So here I will provide you with some demonstration, some programming, some examples that might hopefully then be useful for the next exercise, and also actually anything that you might want to exploit a little further. You have some questions, you have some problems using this or that function or whatever, then you can just tell me. We don't have to do it in advance, we can take it on the fly here and now. If you have any things that you have been wondering about, have problems with whatever actually within this course. Here of course focus will be programming, but it can actually be anything that you want to say have an explanation for, whatever. I mean, you are not that many, so we have time to do whatever we want in these hours. Normally I won't use the full 2 hours, also because I have to run to another room immediately afterwards, so we will be finished a little bit before 2. Hi. Any questions from you before we begin? Any administrative questions or whatever? No? As you see, we do a video of these lectures, so I'll put them out as links on the homepage as soon as I am done. Yeah, that's okay. Hopefully it should be readable. Yeah, should be okay. So today I wanted to play a little around with basic MATLAB. As I understood from the first lecture, all of you have touched MATLAB at least, so we will start not as a novice, but not an experienced user either. Here, feel free to interrupt me with questions anytime. That's quite okay. And also, if you are uncomfortable asking in English, feel free to ask in Norwegian. I have to repeat the question anyway, due to the camera, because I have a microphone but you don't, so whenever you ask me a question I have to repeat it. So okay, then we will start. I mean, you had been fighting with exercise 1 already, and it was successful. Yeah, okay, more or less. So I won't give you that many hints here and now for exercise 1. I mean, you have already done most of it, I guess. I'll address a little bit about this machine epsilon. I'm not sure, did you show them the machine epsilon? No. So that's something that we can play around with. And then I will go further into some demos, examples that you might find useful for exercise number 2. Which then will touch the topic of chaos. Everybody has, I assume now, MATLAB installed on your computers. In these hours, from time to time, I will think ahead, meaning I will put out some MATLAB files that may or may not be complete in advance. Then while you're sitting here, you can download them from its learning and then program with me here and now, if you want to do that. Anyway, everything I do in these lectures will be put out on the homepage on its learning afterwards anyway. So you will find them there later this evening, hopefully. MATLAB. If you want to test your installation, you write bench. Bench, that's a benchmark that then can show you how very, very bad your computer is. So he tests a lot, and then you get your computer, this machine, compared with other machines. So that can be interesting if the salesman that told you the PC you're sitting with told you that, oh, this is a very good machine. Then you can tell, no, it's not. So typically here you have to buy a new one. So this one, actually not too bad, but bench, that's always a good test. Installing MATLAB, you have the option of plenty of toolboxes. Now in this course we don't need that many additional toolboxes. We have one which I'm going to show you later. It's called a PDE tool for partial differential equations. That will be just for demonstration purposes, nothing we are going to need in the course actually. But I would always recommend, when you install the MATLAB, take everything. Steal all the software you can while you're here. We have a lot of good software on the university. Steal everything. Because when you're out in the industry, you won't get anything, I can tell you. It's very expensive. So play around with it while you can. Yeah, we can start here by a new script. How you like the setup with MATLAB? Your choice. Here you sort of have everything in one big window with several sub-windows. Your editor, the command window, and then some additional folders and workspace. Some like to do it like that, others like to have this editor in a separate window to get it bigger. Your choice. You can switch back and forth as you like. But the two things that you need is, of course, the command window and the editor. On some version of MATLAB, you had the effect that when you got an M file, last name M, you double click on it and then only the editor starts. That can be inconvenient because, okay, you get the editor and you get the MATLAB code, but you can't run it. He only starts the editor, he doesn't start MATLAB. So that can be a pain. Because the beauty, when you start MATLAB and then the editor afterwards, then you have a very nice green play button here. That means save and run. But you don't get this button if you do it sort of in the wrong order. Depends on the version, of course. This one is the latest version. I think he starts everything at once, but you never know. So as a general rule, start MATLAB and then start the editor afterwards. And here, when you have the editor up and running, you can give commands here and do whatever you want. And when you want to play them, to run the script, you click this one. First time, of course, he will ask for a name. So on this computer, I have been here before, I think. Never mind that. The first program is called epsilon. And then we have to change the folder. Always change the folder. Don't add to the path. That's a mess. It doesn't work in the end anyway. So just change the folder so you have your working folder where you have your files. And then, of course, you get a whole lot of error messages here because this is wrong. You have now the address where you are working. The working folder. I will always recommend, when you do something in MATLAB, create a new folder every time. Because if you say, okay, in this course I create one folder, TEP4280, and then I put all my MATLAB files there, you're going crazy in the middle of the semester. If you are using the same function names over and over again, you are going to mess it up. So create one folder for each task, like exercise 1. And don't dare use the Norwegian letters. Øving 1, no. He may find it or he may not find it, so I will never trust it. Especially in the folder names as well. No, no, no. File names, folder names, never Norwegian letters. Never, ever. It should be forbidden. First thing you do in any MATLAB script, you say clear all. Destroy everything in memory. This is quite essential actually when you are playing around with MATLAB, because you are allowed to do a lot of things, a lot of crazy things, and MATLAB will accept it, like the value of p, sort of built in 3.14, but no problem to say p equals 17. That is quite okay. Now pi is redefined as something totally crazy, and now if I create a program using pi, he will use 17, and tomorrow I've forgotten all about it, so then you get some strange results. Clear all, he will fix it. I mean, pi now is 17, but with a clear all, then you are back to what you should have. So clear all, always good. Also, I will recommend close all. Close all, he will kill all old figures. And when in your program you have some graphics that he's going to display, he will then display it in front. If you don't have this one, close all, then you have some old figures lying 17 windows behind this one. You don't see them. And when you run, he will update the figures, but you don't put them in front. Then you have no idea what's going on. So close all, then you get the new figures in front immediately. Finally, CLC. Clear the command window, because every time you do something stupid, which you will, then you have a lot of error messages in this window. And from one single execution, you try to run a program, you have a lot of these. Then you have to scroll a little back and forth here to find where is my first error, because typically in a program, it's the first error that counts. So when you are debugging a code, you have to find the first error within the latest run. Now with this CLC, he will clear this window. I can show you. We run, and you see the command window is now clear. And now if you do any mistakes, then you know it's from the latest run, and it's the upmost error message that you have to look into. So CLC, very good idea. What I wanted to play around with as a beginning was the machine epsilon. The machine epsilon is a built-in value. It's called eps. That's the smallest number your computer can say differ from 1. And here it's 2 point something to the power of minus 16. Roughly said, you can have 16 digits accuracy in a number. For us, this can be a real pain actually, because frequently we will have the problem of a lot of calculation, and typically we will have a value x that we now will change with, say, some small adjustments, some delta x. And then we have to do this over and over and over again. X, say, he is of the order 1. And this delta x, he can be very, very, very small. Very, very, very small. Okay, 0.00000, something like that. And when you try to add these two numbers together, well, now it's a question how many digits do the computer use? What's the precision? What's the machine accuracy? So if this delta x becomes too small, smaller than 10 to the power of minus 16, he doesn't see it. So that can be a pain. The default in MATLAB, that is double precision, 16 digits. You can address him with a single precision. Let's say eps equals single eps. Now let's see what happens. Of course, he didn't get that one. We don't see it with eps. He's too hard built in, at least in this version. Never mind. Single precision means he only use 8 digits. Then the machine epsilon will be 10 to the power minus 8. And here you are quite quickly in trouble. 1, 2, 3, 4, 5, 6, 7. Okay, should be okay, but just in the limit. Also, the 1 here can easily be 1 point anything behind this due to the machine accuracy. So it might be quite uncertain. So if with another computer you are using the default, which frequently would be single precision, not double, due to the requirement in memory, then if you have this problem, the delta, well, he can easily be single precision. That's quite okay. The machine can easily give this number quite correct, 1 comma whatever to the power of minus whatever. So he can be a single precision. These guys should then be double precision if you have to do this manipulation. And that's quite common actually in other systems, if you're using languages like C or Fortran or whatever, to have some double precision, some single precision. So here I just wanted to play around with this machine epsilon and see if we can find it. So I start with epsilon equals 1. Here. So now I will try, as long as I can get the difference. So I say while epsilon plus 1, do it like this, is bigger than 1. As long as he can tell the difference there. If epsilon becomes so small that he can't differ between these two expressions, then he should stop. So here I now say eps equals eps divided by 2. So now epsilon becomes smaller and smaller until he is so small that MATLAB doesn't see it anymore. So this is then how we can find the machine epsilon. Then in this logic we have gone 1 too far. We have found the epsilon that is so small that he doesn't see it anymore. Hence we have to go 1 step back. Eps equals eps plus 1. Then he should now print out the same machine accuracy. So here semicolons doesn't give any printout. Here we get the built-in machine accuracy. Here we print out whatever we find. Now it shouldn't be plus 1, sorry. It should be multiplied by 2. Let's see if it works. Yeah. So the first one, that's just the answer to the first machine epsilon, 2.22 minus 16. And the one we find from this loop, you see it's exactly the same. Okay? But then we do it again. So now eps is not only 1, it's single precision 1. Now let's see what happens. Okay. 10 to the power of minus 7. That's what you get for machine accuracy with single precision. So, of course, normally we won't use single at all. The default is double precision. But now, say, how can we check this? Eps is 1. Call him eps number 2 then. Eps 2. Like that. Then I had two different ones. Eps 1 and Eps 2. Or Eps and Eps 2. So you have the values here. Now if you want some more information of them, and this is something you can do for any in any code, any program. So this is just a workspace, but I want more information. You write whos as a command. Whos, then you get a list of your variables, the size. Here, the 1 by 1 matrices, they are just single numbers, but you get the number of bytes, and then you see the single precision. Reduces memory. So if you have a simulation and you blow the memory on your computer, turn everything into single precision, then you have twice as much workspace. That's a trick. Normally we try to avoid it, but sometimes you have to. Unless you buy more memory, of course. Your choice. When you hand in your exercises in this course, we want the MATLAB code, but we would also like to see that it actually works. Now we have 2 student assistants, and they really hate if you upload on this learning as an answer to an exercise 27 different M files. Then they have to download manually each one of them, and then they have to put it on the hard drive, and then they have to test your code to see that it works. They don't like it, I can assure you. So if you want to do all your M files as an answer to an exercise, zip them together, one zip file, and then upload everything. That's one way to do it. Another way, that is to use what is called publish. Publish is a very nice thing. You can actually generate a report from your source code and get one single PDF file with the source code included, together with all the graphics, any printout, and also the figures will be included in one single PDF file. Then you just upload that one. So the publish, it's a little sad with the publish, because by default MATLAB has said create web pages, which is not something that we are interested in. So you have to change the default. And here, publish, you have to check the options, edit publishing options. So here you see the format is said to be HTML. That's web pages. The output folder, that would be an HTML subfolders to wherever you are standing. So the name here, that shouldn't bother you, but don't choose this format. So change this format to PDF. You just click on it and choose PDF. You see you have several other options as well. You can create a Word file, PowerPoint, even LaTeX. So, but for us, I would say PDF. So now we can try to do a publish and see what happens. So he runs the code. Yeah. and you get this PDF file here. This is sort of, if you don't do anything fancy, you get it very simple, your source code, and then the printout at the end. Very easy. And this will be a beauty for the student assistants when they are correcting your exercises. Here they can easily see the code and the answer. And they can even take cut and paste of your code if they have to rerun the case, your programs on their own computer. So use the publish. That's a very good one. If you want to play around with publish, yeah.
Will it also publish figures?
Exactly. Yes, he will. I can show you. Here we have something, and then we plot 1, 1. That should be a dot in a screen somewhere. Let's just hit publish now directly. Ah, he didn't like that. Ah, yeah, that's a nice one. Anybody see what's wrong? He crashed. I tried to publish. He didn't want to do that. Why? Well, he's stupid. That's one reason, but another reason. I was really angry first time I experienced this. Well, the reason is I've done it once. And here I have Adobe opened. So the file is already open. Then it's not possible to overwrite it. So you have to close the PDF reader before you are allowed to do it again. So you have to close this one and then do it all over. Yeah. There you go. So he runs the code. Then you also get the figures on top of everything else. But here now in the PDF file, you have the code, and here the printout, and then finally the graph as well. So yes, and if you have 20 figures, they will come. Okay? So you use the publish. I think the student assistants will love this. And say for your own if you want to do it a little bit more sophisticated, I mean, it's quite typically when you do a program, you write it like this. Straightforward, no comments. Nobody in the world will understand what's going on except you. And after 2 weeks, you have forgotten all about it. So when you find some of your own old codes, you don't know what you were thinking in those days. So you have to do it all over again anyway. So of course, use comments. That's important. And if you want to do it a little bit sophisticated, a comment, that's a percentage, and then a text string, use 2 percentages. Then you can start playing around with this publish thing. First of all, you see when you do 2 percentages, he changed the color of the entire workspace here. Now this one is sort of 1 unit. And the first should be now the headline, so we can call it, say, machine epsilon, and then you can write some more blah 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 here, and then here we say percentage print out default value, like that. Then we wanted to create our own machine epsilon. So then again 2. Now you see what happens. As soon as you hit 2 percentages, now this one becomes yellow in the background. So now this one is a separate block from the first one. And here you can now have a subtitle. So what should we say here? Double precision, just to make it easy. And then the last one here, another 2. and then single precision. Like that. Well, when you now switch windows, you might say, it's sort of sub-windows. Whenever you click into one of these blocks, they sort of become active. So the background color will change, whether depending on where you are inside the code. Now, if you go back to the editor here and click Run, he will run as normal the entire code, no problem there. Well, this figure we don't need anymore, actually. And you get the same printout as before. So nothing has changed in here, the work environment, but you have some comments in the code. Also, you can, if you want, you can just run part of the code. This part that is active, that's actually possible. Should be an option here somewhere. Run epsilon, whatever. I think it was control run, was it? No, I don't remember. It should be possible. You can look it up yourself. The point here is the publish. If you now publish, you will get a report. Even table of contents, machine epsilon, double precision. So you see, you get sort of a very nice report here. And also, if you have, say, a figure in between here, I can show you. Say we create another figure, say here, plot 1, 1, and then publish again. We will now have 2 of these figures, and we get one figure here and then another figure here. So it's fairly straightforward how to use it. If you want to do a little bit more sophisticated use of this, you can have a look in the documentation. Now, the doc pages, actually they are quite good, so there is where you learn MATLAB. You don't buy a MATLAB book, you play around with it yourself and you use the documentation. The doc system is very, very good indeed. So, doc publish, you should have plenty of idea what you can obtain here, how you can use this documentation. You can create lists, you can do this, you can do that. So have a look if you want to do it more sophisticated. But I mean, we shouldn't overdo it. I would say whatever we have done so far will be quite enough in this course. Okay, any questions to this one? That's okay. Good. Okay, then I wanted to play around with an example. And let's just check that it becomes a part of the video, sorry, so it doesn't miss it. No, it's not. He should be there. As an example, we look at planet orbits. Planetary orbits, fairly simple problem. You have the sun, and then you have the earth, and then you have a force, and the force should then be, gravitational force should be negative if you have the origo in the sun, should be then in the negative radial direction, and the force, the magnitude, should then be the universal gravitational constant multiplied with the mass of the sun, big M, then the mass of the planet, small m, divided by distance square. So here you have the radius. And then, to be correct, and unit vector in the radial direction. Find the motion. Describe how this planet will move around the sun. Okay. Then we are going to need another law, which then says force, sum of forces acting on the mass equals mass times acceleration. That should be the Newton's second law of motion. And here, what will we get? Well, first of all, this constant, the mass of the sun, and then the universal gravity constants. Of course, this is what we will baptize to a small little g, 9.8 or whatever. Here I just keep it as a variable. Also the mass of the Earth, very big number, so here I'm going to use unity anyway. But just keep them for now. But Newton's second law should now read mass times acceleration equals the force equals, and then gm, small m, radius square in the radial direction. And here the small m can be skipped. So it doesn't matter how heavy the planet is, or if it's you could be also think of it as just a satellite around the Earth. It would be exactly the same problem actually. Now we want to program this motion, this behavior. How can we do that? Well, at the first glance, it sort of looks like we have to do this in polar coordinates. We have the R position. I don't want to do that. I want to use Cartesian. So what do? Well, we split it up then into our x and y components, this one. Now the acceleration will now be the derivative of the velocity vector, and then again the double derivative of the position, as everybody knows from mechanics. So when I split this one up, I will have to split it up into the x and then the y position. I need the x velocity and the y velocity, little u and little v. That should be convenient here. But how to split this one up into x and y doesn't look promising. R, that should be the square root of x square plus y square. Not so funny to split up, is it? But we can do a little trick here. Say the acceleration in the x direction now equals time derivative of the velocity in the x direction equals. Then we do it like this, minus gm over radius square. And then I have to pick the x component. So a trick, multiply with r up and down here. So then we have r to the power of 3 beneath, And then above, I will have an R, which I then pick only the x component. That's a nice trick. Then, of course, you do the same in y direction. Here it's small v, dt, gm, and then we write it like this, of course, r3 multiplied with y. Very easy way to split up this radial force into x and y components. And here we will call this one u with a dot above, and here v with a dot above. So this will now be two ordinary differential equations, but it's not enough, is it? So what will our total equation system be? Well, we have to sort of define our two velocities as well. So we have to write the following. X dot is defined as the velocity in the y direction, and y dot, well, that's the velocity in the y direction. Yeah, x in the u in the x direction, v in the y direction. We do it like this instead of writing, which also we could have done. This one is x double derivative. This one is y double derivative. But we never like double derivatives. We have to use first order equations, much easier. Double, nah, that's tricky. So we should write them as a set of first order equations. So here then I have four ordinary differential equations. They are coupled. The x's and y's goes in everywhere, also in this r, remember, the position, square root of x squared plus y squared. So it's quite a nonlinear equation system. Program it, solve it. You have the break to do it. Any questions? Then we take a break.